Okay, so hi everyone, Senan this side, and in this video we are going to see how do we solve this. Find the student that will replace the chalk. So in this, I'll show you three solutions. Okay, two of them would be working just fine. The third one would give you a time limit exceeded. So, but all of them do work, and that is why we are going to discuss all of them with a dry run on a notebook with a pen. So let's first discuss what the question is exactly asking us to do. So you are given n students in a class, right, numbered from 0 to n minus 1. So 0 based indexing. So given the array, the index would determine which student are we talking about. Okay, so teacher will give each student a problem starting with the student number 0, okay, and the student number 1 and so on. Okay, so first the chances, so teacher will assign the first problem to student 0, then student 1, 2, 3 until the time the teacher reaches n minus 1. After that, the teacher will again cycle or restart the process starting from 0 again. So this is restarting the process starting from 0 again. Okay, we are good with that. You are given a 0 indexed array, chalk, and an integer k, and there are initially k pieces of chalk. When the student number I is given a problem to solve, they will use chalk of I. So given chalk of I denotes the number of chalk used by the ith student to solve the particular problem. Pieces of chalk that's all. However, if the current number of chalk pieces is strictly less than chalk of I, then the student number I will be asked to replace the chalk. So whoever finishes the chalk, or the person who is not able to completely solve the problem with the given chalk, we have to return that student, and by returning that student we need to return the index of that student. So given this test case, I'll just go through a dry run on my notebook and we'll see what we can do about it. Okay, so here we are. The very first test case that we have is this one, right? And I'll show you everything on this, and this is a perfectly good test case. So what we will do first is, okay, so I is pointing somewhere which is not inside the array itself. So what I'll do is I'll take the array of I'll give the chance to the 0th student, right? So let me just number the students. So this is student 0, this is student 1, and this is student 2. So what we are given is this student I, right? We have currently 22 chalks. Now it's the turn of student I, which is student of 0, and we need to figure out which student will actually do the replacing of the chalk. Okay, so we are good with this. So what I'll do is, since I'm seeing the student requires 5 chalk, so I'll say hypothetically I'll assume this student solved the problem which whatever was given to him, and 22 minus 5 is what? 17. So now I have 17 chalks, and I'll pass the turn to the next student. Okay, so this student uses exactly 1 chalk, right? So since this is using exactly 1 chalk, what I'll do is I'll assume he solved the problem, and now the number of chalk is 16 with me, and I'll move the iterator, or I'll give the chance to the next student. Okay, we are fine till here as well. So what I am seeing is, okay, so we are at student 2 again, or not again, but student 2 for the very first time, and he utilizes 5 chalks. So I'll say utilize all the 5 chalks that you have, and we return to what? 16 minus 5 is 11. Now we are good with this, right? We know that student 2 has solved, and we try to go ahead, and since we go ahead, we cycle back to the very first student, right? We can cycle back. Okay, now I see this guy uses, the student 0 uses 5 chalk. So what I'll do is I'll take this 11, and I'll have 6 chalks left, and I'll pass the turn to the next student. Okay, now I see student 1 uses exactly 1 chalk. So what I'll do is I'll utilize that chalk, and I would have 5 chalks left, and I'll take this iterator, I'll push this one step ahead. Okay, now I see student 2 uses 5 chalks, and how many chalks do we have? We have exactly 5 chalks. So what I'll do is I'll use all those 5 chalks, and I'll be having exactly 0 chalks. Now what I'll do is I'll take this iterator again and go back to the 0th. Now this is where the problem is going to start. Now what you see is student 0, right? Student 0 has how many chalks required? So student 0 has 5 chalks required by him, and we have 0 chalks. So what does this mean? This means that I cannot process this student, or the student cannot solve the problem given the chalk he requires. So what I'll do is what student 2 will do, he will try to replace the stock of the chalk. So he'll replace this chalk itself. So that means we need to return this 0. We need to return this because this is the student that will be doing the replacing of the chalk. I hope you get the point, you understand this, and let's go and look through the code of how do we actually implement this, and then we'll try to proceed to a better solution. Okay, so here we are back in my laptop, and if I'll initialize this I to -1, so way before the the indexed -1, so zero based indexing, right? So now I say n is equal to chalk.size. I get the number of chalks, a number of students. Now what I do is I see n while k is greater than 0, that means I still have some chalk remaining, and what I'll try to do, I'll give this turn to the next person, right? So it's -1, so now I'll give this turn to the 0th student. After doing that, I'll subtract the number of chalk he used, and I'll go to the next iteration, and till the time my k is greater than equal to 0, that means I can still process the chalks, right? So I give the chance next to the next student, to the next student, and if you see this I, this modulo n is for cycling back to the first student. So you increment the pointer and you cycle back to the first location. So that is basically how you traverse this array in a cyclic form. Okay, so let's say if for some reason at any point k becomes negative, so that means if k is negative, we were not able to process the student I, right? We were not able to process this. So that means this I, this ith student will be the one who will be replacing the chalk, and that is why we break out of this while loop, because k is negative and then we return I. So there are some assumptions. Chalk of I is never negative, right? So this value would increase, and it also does not make any sense. And in the worst case, in the worst possible case, if everyone uses one chalk and you have a million, let's say you have a million chalks remaining or a billion chalks remaining, and everyone uses a single chalk, so you'll iterate over the list like a couple of billion times, right? Let's say if the size of the array is, let's say you have 1,000 students and every student takes exactly one chalk to solve, you will still have to do a million iterations over the while loop. So that is because of which we could lead to a time limit exceed. So this is the obvious, the brute force approach, the logical approach, and the worst case is big O of, the worst case scenario is big O of k, at least because I am since you see k is at least one, chalk of I is at least one, n is at least one, right? So the minimum value of this is 1, but if you see the worst possible case could, every chalk of I is 1, k is a billion, right? 10 to the power 9, k could be a billion, and that could lead to a time limit exceeded. Even if you have a single child, you have to go through that single element a billion times just to make sure that will he be the one who will do the replacing. Okay, so now how do we improve this? So the next would be what I would say the optimal approach, and the last one that I'll be showing you is just for fun. So let's see the very next approach. Okay, so here we are back in my notebook again. I'll just clear everything, or yeah, just clear everything. And this was the initial position, right? This I place this here, and now if you observe, if let's first of all do the summation. So 5 plus 1 plus 5 is what? Is 11. So I know at every iteration, I'll use 11 chalks, and if somewhere I have less than 11 chalks, in that iteration I would get to know the answer. Again, I'll do this again. The sum is equal to 11. Since the sum is 11, that means the thing is that this thing, every iteration that we make, so in this case we went like this, and then we came back, then went again a different the second iteration, and when we came back for the third iteration, at that point of time we know that at this position we will be out of stock of chalk. So that is the whole point. Since I have this value of sum, what I could do is I can first calculate the number of iterations I would have to go through this before I get to the iteration in which I would actually find a solution. So what I'll do is first I'll calculate this sum. What I'll do is k is equal to k modulo sum, and this is the operation that I'm going to use. The whole idea is exactly the same, and so I'll say since sum is 11, I'll say k is equal to 22 modulo 11, which is exactly 0. So rather than doing this whole iteration twice before finding this is the place where we are having some discrepancies, some issues, I'll just do the mathematical calculation, and I'll say that k, or k divided by sum, is the number of iteration that I'll just go throughout the loop without finding a particular any solution, right? So this is the idea, this is the logic. So I'll just update this k value to k modulo sum, and this would give me, so the very first iteration would give me the solution. So clearly I'll just remove all of this. So what I'm left with is not this, k is equal to 0, and we are starting our solution exactly from this. So now what I do is I take this I go to this 0th student and I'll say solve the problem, and student be like, I need 5 chalks, give me 5 chalks. The teacher is like, I only have 0 chalks. So teacher is like, you replace the chalk. And so in the first step itself, we know that it's the 0th guy that has to replace the chalk. And yep, that is the whole point. And this is exactly what you'll implement. And this is exactly what you'll implement. And this is what you are expected to do in this problem, right? And this is this second iteration. So what you see is this, the same code, right? The same code that I had here. We have the same thing, just one more additional thing is we calculate the sum of all the elements and then do the modulo operation with k and do the same while loop and return I, right? So the only extra step is this one, you update the k, otherwise everything is same, and this would heavily increase the number of iterations that you do. So what is the time complexity? Time complexity for this one, we discuss it's big of k. For this one it will be what? It will be big of n, the number of students, right? And for adding, and again big of n for searching the student, so big of 2n, approximately close to big of 2n, and that is what we are going to learn. So this is a linear time complexity with a constant space. Fine. Now the last approach is not something I'll show you through the chalk, but I mean not through the chalk on the notebook sheet. What I'll do is I'll just explain you, because this is working but this is not as optimal as it may seem. So I just found that to be helpful. So let's look at this. Now rather than having a single element of prefix sum, I say the sum, I have a list of prefix sum. And what I'll do is I'll add all of these elements, and keep that in mind. I've used long in this as well because the sum could exceed. So if you see n is 10 to the power 5 and chalk of I is 10 to the power 5. So if you multiply both of them, you'll get 10 to the power 10, which is something way beyond an integer could store. So that is why we used long. So I keep a list of long of n students, and I calculate the prefix sum. And in the end, I again do this k modulo sum. So last element of this prefix sum would contain the sum of all elements, right? So this is k is equal to k modulo the total sum, and I'll just do the upper bound calculation, and I'll take the modulo and I would get the final answer. So what is this upper bound? Upper bound is in this prefix sum begin and end, I mean prefix sum list, you find the number that is just greater than k, which is not k, right? The location of or basically it would find the student at which he would not be able to process k elements, and in the end you do the modulo operation with the final index and you return that. The reason I'm not explaining this because not everyone is comfortable or knows what is this upper bound, but just so you know, when you are doing the prefix sum, right, the prefix sum is every number would be greater than the previous number, right? So this prefix sum, this list is already in a sorted order. If you realize that this list is in a sorted order, so to find an element, what I could do is just use binary search. So this will do the binary search and find the element which is just which is greater than the x, greater than k basically, and not which is not k as well. And this would give me an iterator, and I'll subtract the first iterator from this as well. So this would actually give me the index of the student or the number of student, and it could be possible that the student could be the last student. So what I'll do is I'll take a modulo with n and I'll just return the answer. So for calculating the prefix sum, the time complexity is big of n and space complexity is also big of n, which is why you should not do this, but this was a bit interesting to involve binary search as well. So this is big of n space, this big of n time, and this is log n time. So the final time complexity and space complexity is both big of n, and this is working well. See, just the case is I just checked for a corner case, which is that you only have a single element, and that's the point where you could actually do some error you can get some error. So that was the corner case for me. This is accepted as well. So yep, that was the whole video all about. Hope you were able to understand this. I showed you three solutions. The first one will give you time limit exceeded. The second one is the optimal approach, which big of n space or big of n time with constant space. And the final solution that I showed you just for fun, which is big of n time and space, but we are somehow involving binary search in this as well. So yep, that was the whole video. Hope you enjoyed this, and I'll see you in the next video.